So yeah, so this is going to be shared. I'll email this to you guys. And then the word bank is going to be exactly as it is. So hopefully those help, at least targeting like different terms that you should know. I don't think that you should dictate all of your setting just off the terms that are in the bank. These are the ones I think that are probably most important, but obviously anything else that we've talked about term-wise might pop up in other questions. So example being, we don't have independent or dependent variables listed in this word bank, but you definitely need to know how to identify those. So, okay. So for the exam, it's going to be broken up into sections. The first one is terminology. So this is where you'll use the word bank. The next part, usually I'll give you guys some type of conceptual scenario. Later in the semester, the demands in this section will be a little bit greater, but because we haven't really done a whole bunch of stuff with regards to like research design or research questions, this area is pretty much just going to be limited to types of data as well as identifying different variables. You'll have a written calculation section. So this first section is probably the most heavy on handwritten calculations. After this test, usually I kind of get rid of this section unless I highlight a certain formula or whatnot in the actual lecture series for that given exam. And then the heaviest part of the exam is going to be based on Excel or SPSS data. You should be able to perform all of the calculations on this particular test in Excel alone. So I kind of do that if people are still having issues with SPSS or something. It kind of gives them a little bit more time to figure stuff out. But this is where reviewing your activities is going to come like super in handy. So I would probably say a good 40% of the exam points are going to be based off of Excel calculations and organizing data, or at least using Excel at some capacity to answer questions. So I would focus your concentrations not solely on like reviewing activities or going back through the procedures that you used for them, but just like that's where the big emphasis of the test is, because that's where you guys do the most stuff. Okay. All right. Any questions before we get started? I know there's like a lot of notes, but I just want to make sure I cover all my bases. I think we're good.
Do we have to write anything or type anything in Excel in this exam, or just it's going to be just answering and typing question in the data sheet?
That's a great question. So the Excel sheet is all yours. That's like a blank page of workspace, pretty much. I mean, it's not completely blank because obviously there's data in there, but you don't have to submit it as a part of your grade. It's just basically filling in questions. Kind of the exam largely mimics like a free response exam, which is what I usually have given in the past. So some questions will like auto grade themselves, but pretty much all you're turning in is that like quiz submission, and that's it.
Yeah. Okay.
Cool. All right, so let's start with the word bank or the terminology section, and you guys can feel free to put answers in the chat, or you can yell stuff out. I mean, not yell, but like say what you think the answer is. So the first one we're looking at is finding an individual's percentile for a 1RM squat is a way to blank them.
Or measure them.
The 1RM squat could be a measurement in the test, or in the sense that maybe like we're looking at how much weight they could lift. Right? The squat itself is a test But if we're looking at an individual's percentile, that's kind of the key focus of this one.
To evaluate them?
Evaluate, there we go. Okay, so it's a way to evaluate people. Remember, we can use percentiles to compare people to other people, right? But a percentile is an evaluation method, right? Because we're looking at one person in a scale of scores that have been collected. Okay, so I'm gonna put these in red and I'll type answers as we go. So we're evaluating, right? And that's one thing to note about the word bank is some of the words have to be changed slightly to be grammatically correct. So some people are like, evaluation, that might sound right, but it doesn't sound right. I don't know. Anyways, there's only so many ways that I can write stuff in the table. Okay. This next one is going to be body composition is a type of blank, while hydrostatic weighing, bioelectrical impedance, and skin folds are different blank to quantify body composition. So what do we think this first one is going to be?
Non-random sampling?
Not quite. Jericho put measure in the chat, and that's what we're looking for, right? Body composition is a type of measurement. We haven't put units to it, but it's type of measurement, okay? Hydrostatic weighing, bioelectrical impedance, and skin folds are different what?
Are they different tests?
Yeah, those are different tests, right? They're different ways or methods in which we can acquire the measurement of body composition. Okay. Now I want it bold and underlined. Right? So they're different tests. Okay. All right. So number 3, inexperienced undergrads aren't likely to be as graduate students when it comes to marker placement.
Reliable.
Yep, reliable. What is reliability referring to?
Their skill level.
Could be skill level, right? But it more so reflects the accuracy. Okay. I noticed Isaac also said valid, right? And a lot of times when I ask these questions, sometimes there's more than one correct answer. Okay. So yeah, Vinny, you're correct. Ability to repeat with accuracy, right? But again, reliability is with relations to consistency of measurements, and validity is looking at accuracy. But in relation to what we just talked about, number 4 says finding joint angles using video or motion capture is more what than using a manual goniometer. Yeah, so Chris, you chimed in and you said valid, and that would be correct, right? Because now we're looking at the accuracy, right, of equipment. So I think tests, measurement, and evaluations are 3 terms that you want to be able to distinguish between, and then validity, objectivity, and reliability are 3 that you want to be able to distinguish between, okay? In a group frequency distribution, the blank size is determined by taking the difference between 2 adjacent upper or lower bounds of groups. What do you guys think that is?
Is it interval?
Yep, interval. Okay. So that's like this little I, right, in our group frequency distribution. It's a constant based on the groupings that we're working with. Okay. Number 6, a researcher not treating subjects the same is an example of blank and affects what type of validity?
Objective.
And this is another one that could have potentially multiple answers, right? So researcher not treating people the same could mean that there's something wrong with their objectivity. Think of the way that I try to direct this question is it's affecting some type of validity. So what are the factors that affect internal or external validity. If it has to do with the investigator.
So investigator error
Mm-hmm.
and then internal validity.
There we go. Right, so someone not treating their subjects the same way, either maybe they're using different measurement or different tests to gain measurements, or they're falsifying data or something, right? That means we have some level of investigator error, and this is going to contribute to internal validity, right? Internal validity, remember, is referring to the design of the study, right, or different flaws within the study that could potentially affect the outcomes. So the other examples we had of this were learning effects. We also have extraneous variables, instrument error, right? Different from external validity. External validity is going to look at how generalizable our results are to the population that we drew our sample from. Okay. Next one, the blank can be used to compare the variability of data from different units of measurement.
Coefficient of variation.
Coefficient of variation. So this is one of our variability measures that we talked about last week, right? Where we turn basically variability measurements into percentages, and then we can compare percentages of different units of measurement to see which measurement has more or less variability than another. Okay. A researcher studying the effects of low cadence cycling on time trial performance for master athletes only had elite males volunteer for their study. This is a problem with what?
Is it sample or population? Neither.
Not necessarily, no. But you can use that concept to think of what's wrong with the sample and how is that affecting something with regards to the study. Carolina, not quite. So if our target population, we're studying trial or low cadence cycling on time trial performance for master athletes, but we only collect elite males.
Validity.
Huh?
Validity only.
More specific?
External validity.
There we go. Right? It's going to be a problem with external validity. Reason being that our sample we've collected isn't representative of the population we're trying to target. Right? So in order to figure out how these effects are applying to master athletes, we would need not only males, but also females as well, right? So kind of looking into the specifics of the question, and does our sample answer that question? Okay. Number 9 says, in data that is normally distributed, the mean is likely to be greater than, less than, or equal to the mean.
Equal to.
Equal to, right? Perfectly distributed data basically says our mean, median, and mode, right? All three of our measures of central tendency are going to be the same. Okay. We would calculate a blank when estimating a population percentile for a given raw score in a sample. There's 2 different ways we can calculate, right, percentiles, and yeah, Isaac just popped in the chat z-score. Okay, so that's one distinction I wanted to make, is that anytime you see estimate percentile, you're going to automatically go towards z-score. Okay, and the reason that we call it an estimation is because z-scores are based off of perfectly normal distributions, which is what we assume the population looks like, right? We don't always know if our samples are normally distributed. So if we use a z-score to estimate a percentile for either a population or for a score within a sample, we have to use, we're using a z-score on the basis that we're assuming our sample or our population is normally distributed, okay? When you're looking for an exact percentile within a given population or a sample, it's regardless of the distribution shape, right? It's kind of just like, well, these were the measurements that we collected. Where does a given raw score land within that set of measurements, right? And they can be negatively skewed, they could be positively kurtosed. It doesn't really matter what the shape is. You just want to know what is a single raw score within a given set of scores from a sample. Okay, so exact percentiles are going to be when you use your distribution or your frequency distribution calculation. So these two up here, right? So then we go into our conceptual scenario, right? So I've given you a research question. Let's say you're the researcher, okay? And I say, what is the effect of carbohydrate, caffeine, and carbohydrate plus caffeine mouth rinsing on intermittent running performance in collegiate male lacrosse athletes? So what is the independent variable or variables in this research question?
Carbs, caffeine, and carbs and caffeine.
Right? So it's basically the mouth rinsing solution that we're using. Right, or we could say type of mouth rinsing solution. That might be better. Okay, so we split this independent variable up into 3 different categories, right? Carbohydrate, caffeine, and carbohydrate plus caffeine. So what type of data would this independent variable represent? Yeah, Jericho, you put in the chat, it's nominal. Okay, because we're dividing people based on category, right, or level, right, depending on the type of mouth rinsing solution they're given. Okay, what would the dependent variable or variables be in this situation?
Running performance.
Yeah, so running performance, right, and then you can kind of get an idea of how we might evaluate running performance or test it. So what type of data might we get from that?
Ratio.
Right, because we could say how long does it take somebody to run, right? Do they run faster when they have caffeine or carbohydrates or both, right? And time is an example of ratio data, okay? You could also look at reaction time, right? Maybe like how fast do they respond to, you know, a start gun or something. I don't know. It kind of just depends on how you're measuring running performance, right? But typically we would get some type of ratio measurement. Okay. In this next part, what's the hypothesis that is statistically tested for this study? First, I want you to identify the technical name of the hypothesis, and then we're going to write it out.
Would it be the null hypothesis?
Exactly, right? So we have a null hypothesis and we have a research hypothesis. So whenever we statistically test, right, any given research question and data that's been collected, we have to test the null hypothesis, right? Because everything is innocent until proven guilty. Okay. And then what would the null hypothesis be for this specific example?
The type of mouth rinsing solution has no effect on running performance.
Yep. And we can be as simple as that, right? We can just say type of mouth rinsing solution has no effect on running performance. So null hypothesis always says there's no effect, no relationship. So now let's relate this to a p-value, right? If we said the results show there is a significant difference between mouth rinsing solutions with a p less than 0.01, what would this mean First off, would we accept or reject the null hypothesis?
We reject the null hypothesis.
We reject the null, right? And that's because this less than is kind of our key trigger, right? Again, this 0.01, that's the amount of error we're willing to accept. So if P says that there's a low amount of error, we're going to reject the null, right? And that would mean that type of mouth rinsing, did I spell that right? Yes, I did. Solution has a significant effect on running performance. Okay. So if we reject the null, that means we accept the research hypothesis, which is exactly opposite of the null hypothesis. So then we go to our written calculations, right? And this might be something that I give you in an Excel sheet, but whenever you see something where you're having to use calculations, it's always good to just type out the work that you did just for partial credit, okay? So first off, what type of distribution are we looking at?
Grouped frequency.
Yeah, group frequency, okay? So group frequency distribution, okay? And then if we're using a group frequency distribution, what percentile does a value of 27.2 inches have? And the question you should really ask yourself is, what missing information or what information do I need to figure this out? Right, so the first thing that we want to do is create insert columns to the left. Just kidding. Not what I wanted. To the right. La 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 la. Right. So we need a cumulative frequency column. That's important. Okay. How do we figure out what the cumulative frequency is?
We just add the numbers as we go down.
And where would we start?
2.
At 2, right? The frequency, so the worst measurement, right? Or the lowest measurement in this case. So that would be 2, right? And then we add on to that. So 2 plus 4 is 6, plus 8, 14, plus 11, 25, plus 14 is 39, plus 20, 59, plus 12, 71, plus 10 would be 81, plus 5 would be 86, plus 9 would give us 95, plus 5 would be 100. So what's our sample size?
100.
100, right? Sample size is always going to be what the cumulative frequency is at the last grouping that we have, right? So with this information, I'm going to pop over into Excel really quick. I'm just going to use this area over here. So in our equation, right, it's going to be, I'm going to type this out. It's 4, right? It's going to be our raw score minus the lower bound, right, of the group that we're in. Okay. That's going to be divided by the interval size. That'll be multiplied by the frequency. And then we add the cumulative frequency of the group worse than the group we're looking at, all divided by total number of subjects times 100 to get our percentile. I'm gonna zoom in. Sorry, that was kind of small. Okay, so if we're putting this into a calculation, right, what is our raw score of interest here?
27.2.
27.2. And what's the lower bound that we're working with?
26.
26, right? Because 27.2 lies within this region. Okay. What's our interval size?
2.
2, right? So we could take two adjacent lower bounds and say 26 minus 24 is 2. All right. And then we multiply by the frequency in that grouping. So that would give us 10, right? Plus the cumulative frequency of the group worse than, where 27.2 would be. So cumulative frequency we're entering is
71.
71 divided by 100. That's our sample size, right? So that kind of completes our general equation, and then we can multiply by 100 to get our percentile, right? So we should get roughly 77%, or the 77th percentile. Okay. Right, so this is an exact percentile. I can highlight that over here. Exact percentile. Okay, because we're only interested in the information from our given sample. Given this figure, we want to know what the median of the data set is within this information. So, do you guys remember how to find the median?
Yeah, it's the middle value.
A middle value when we have our data ordered, right, from smallest to largest. So I'm going to get rid of this. There's a couple ways that you can do this. You can count, right, and say there's 1, 2, 3, 4, 6, 8, 10, 12, 15, 18, 23, 29, and this is where my math sucks, right? But you could count, right, how many, like count all your frequencies together and figure out how many measurements were taken. And then you can just find where that middle number is. Okay. You could also list out all of your data in Excel. So in this case, like our first value is 12 and there's only one 12, right? There are 0 13s and then we have 1 14, 1 16, 1 17, whoops. We have 2 18s, 2 19s, 2 20s, 2 21s, 3 22s, same thing with 23s. There are 5 24s, 2, 3, 4, 5. There are 6 25s, 2, 3, 4, 5, 6. Right, so we could list all of our numbers out this way as well. 2, 3, 4, 5, 6, 4 27s, 2 28s. Right, and then what we can do with this information is we can say what's the median by using a function in Excel. Okay, so in either case, we should get something like 24. Does that make sense?
Yes.
Assuming that I got all my numbers counted correctly.
Aren't we just calculating the lines and then figuring out the median, or we have to calculate the numbers of that frequency? You get what I'm saying?
Yes. So the frequency is just indicating how many times that given number appears in the distribution. So that's why I listed 12 one time, 14 one time. If you look at 21, it's in there twice. So given that all of these are listed the correct number of times and I didn't make a mistake, which is totally possible, but we take the median value, so what number lies in the middle of all of these, right? And one way we can figure that out is by saying, like, how many total values have been collected. In this case, there's 41. So the middle value, right, 41 divided by 2 approximately, right? So about 20 numbers in is going to be where our median value is. Does that make sense?
Yeah.
Yeah. Okay. How would we find the mean of the data shown?
Equal average and then use all that data set.
Yep, so we could do equals average, and then we can calculate the mean through there, right? Usually on the exam, I'll tell you like, oh, give me like the second decimal place or the third or something. So in this case, let's say we're looking for the second or the 100th place, right? We'll say, oh, the mean is 22.93. Okay, so in this case, we've got 24 is the median, and 22.93 is our mean. Okay. Using that information, or just visually, do we have positive skewness, negative skewness, or a relatively normal graph or distribution?
Negative skewness?
We have negative skewness, right? How do you know?
The means push towards the left end.
The mean is pushed towards the left end, or if you think about wherever the mean would exist in this data, in terms of negative standard deviations are on this side, positive standard deviations are on this side, right? So the tail is going to be on the negative end. At least that's how I remember it, right? So visually we know, and there's a couple of answers. So I think, was it Chris who just spoke? You could tell based off of like the mean, right? Visually, we could also say the tail is on the left. Okay. How would we know based on distribution shape calculations? Someone put in the chat. Finding the z-score. Not quite, but kind of. If you're talking about z-score for percentile, then no. But if you're talking about z-score for skewness or kurtosis, then yes. Okay, so remember, skewness and kurtosis are calculations that we can perform to figure out the shape of our distribution. So since we're looking at skewness in this case, right, in order to calculate skewness and kurtosis, we need the sample skewness, right? Convert it to relating to some type of population by using a standard error. And then we can find the z-score of skewness, which is basically our standardized way of saying, does our sample match our population? Okay. So how do we find sample skewness? Does anybody know that one? Got the first part in. Equals what?
Skewness.
Yep. So it literally equals skew, right? And then we could put all of our data in there. Okay. And then how do we find the standard error?
Square.
Sample, yeah.
Good, I heard a square part, right? So we do square root
6, right?
of 6. Yep, 6 is what we use for skewness, divided by,
The count of
right,
the
how many
numbers.
right, how many people we have within our distribution, right? So I like to use the count function. I think it's easy to use. Okay, and then what do we do to find the z-score? For skewness specifically.
Yeah.
Hmm?
Divide the
Yeah,
top
we
by the
divide.
bottom.
Exactly. So the sample skewness is our numerator. Standard error is going to be our denominator. Okay. And we get this score of negative 2.6581. Blah, 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 blah. Okay. What are we looking for? Or what do we want if we have a normal distribution?
Greater than -2.
If we have a normal distribution.
Well, within -2 and 2.
There we go. Okay. So in order for us to say that our sample is, let's see if this will work. Oh my God, I'm trying so hard, you guys. If this is our, oof, God, here we go. If this is our sample, right? And we're trying to say it is the same as our population, okay? Our sample value for our z-score of skewness needs to land between +2 and -2, okay? If we are not in this region, that means our sample is way too positively skewed or way too negatively skewed to be considered normal. So in this case, right, how do we know our distribution shape based on calculations? Or how can we assume we have a negatively skewed data based on our calculations?
The tail is on the left side.
Right, it's negatively skewed because this value lands in this area, right? And if this is our population distribution, that means our sample is so skewed, or it's skewed enough that it's not representative of our population, right? Because it lands outside of this -2 and +2 acceptance area, okay? So if our sample landed between here, sorry, excuse my poor drawing skills, right? If our sample skewness or z-score of skewness ended up landing in this area, we would end up saying that the distribution is relatively normal, right? But because our sample got a z-score of skewness outside of that boundary, right, we say in this case it's on the negative side, so we would say that we are negative skewness because the z-score of skewness is not within the acceptable boundary of plus or -2. Z-scores or standard deviations, either one works, right? If this was positive 2.65, then we would say it's positively skewed, right? So just changing the sign, positive z-score that's above 2 would indicate positive skewness. Negative z-score below -2, right, is going to be negative skewness. Same thing goes for kurtosis, right? If this wasn't skewness and we were doing kurtosis instead, negative z-score of kurtosis would mean we have negative kurtosis. Positive z-score of kurtosis would mean we have positive kurtosis. Anything in between -2 and +2 is relatively normal. Okay. So hopefully that makes sense. I feel like this is the part that people usually get messed up on, or they'll just look at the sample skewness and forget to divide it by standard error. So remember, when you're evaluating shape of a distribution, you have to look at the z-score of skewness or kurtosis based on the question I'm asking, because usually I'll be a little bit more specific. Okay. So what would the exact percentile for someone with a Planck time of 151 seconds within the sample be? Right. So we're looking at Planck time. We want exact percentile. So what type of equation would we use? Remember, when we're finding percentiles, we can either use our frequency distribution calculations, or we can use a z-score calculation. So we want an exact percentile.
The frequency distribution.
Right, we have to use our frequency distribution one. So that's where we need some raw score, the cumulative frequency that exists at that raw score, as well as the total number of measurements we have, right? So in this case, we're saying raw score is 151 seconds, right? What's a way we can find our cumulative frequency at this given score?
Equal count.
Close.
Ifs.
There we go. You have to use a count if function, right? So would a lower Planck time be better or worse than a higher Planck time?
Lower Planck time's worse.
Lower Planck time is worse, right? So identifying what is good, what is bad. is critical for finding cumulative frequency this way. Okay, so we're going to use a count if function for our given range of Planck times. Okay, and then our criteria would be
Less than or equal to?
there
Less
we
than-
go. We want values that are less than or equal to quotation, nope, no comma, and right, whatever our raw score is, and now it's magically disappeared, so you can see this box in red up here. Okay, so any values that are less than or equal to or worse than or equal to 151. Okay, so that would give us 61. So what do we do with this information now? Or actually, how many people do we have total? I skipped ahead, sorry.
Count.
This one we can figure out using a count function. Okay, so we have 93 people, and we want the percentile.
151 divided by 93 times 100?
Not quite. 151 is what the raw score we're interested in. But the cumulative frequency at that raw score is 61. So 61 people out of 93 performed at or worse than this percentile.
Is it X minus cumulative frequency over N?
Not quite. So we go back up here.
Oh, it is.
This one here, right? So cumulative frequency at a given score is going to be 61 divided by total number, which is 93 times 100. This is why I give you guys the formulas, because there's way too many in this class to try to remember. Okay, but that should give us our percentile for this individual. So I'm going to scroll back down. All right, so exact percentile. Let's round again to the 100th place. We would say this person is at the 65.59th percentile. It's wording horrible, but answer 65.59%. Okay. How many people can bench press between 110% and 119.9% of their body weight? How might we go about figuring this out?
Would we do a count if again?
But more specifically, a count ifs, because we're going to have two different sets of criteria.
Okay.
Okay. So one thing that I did on purpose was I put between 110 and 119.9. On the exam, if I did this, I would have to specify if you're including both of these numbers. Okay, so in this case, we're going to include both 110 and 119.9. Okay, and I know on the exam question that is kind of similar to this. I specify. So we can use a count ifs function because we're inserting multiple criteria. We're doing our bench press. Okay, so that'll be our range. And then what's our first set of criteria we're interested in?
Greater than?
Yeah, greater than or equal to
110.
110. And then our second set of criteria is still same cell range, so B2 to B94. And that criteria would be less than or equal to. And
119.
Yep, 119.9. Okay. So again, less than or equal to and greater than or equal to include both of these values. Okay. So that would mean we have 34 people. Okay. We'll put that as our answer. Okay. Which class measurement has the most variability? How would we figure that out?
We can compare standard deviation, maybe?
Okay. You're getting there.
Very.
We do have to calculate standard deviation. But how can we turn that into a standard score so we can compare all of these different measurements of or units of measurement together?
Z-scores?
Not quite. That is a
Very.
standard score.
Do we use the variance formula?
Variance would just be a square of standard deviation, so that wouldn't really be giving us much different information. This is good. These are very good guesses, you guys. If we go back to our terminology questions, what did we say on this one? Coefficient of variation can be used to compare the variability of data from different units of measurement. So coefficient of variation is what we need to calculate. And this is the way that we calculate it. So calculating standard deviation, and we also need to calculate the mean, right? So you kind of have to think about, like, is there hidden definitions in the question, right? And then what would you have to calculate to get that stuff? So we need standard deviation, we need the mean, and we can divide those two to get us our coefficient of variation. Right, so we can do this for push-ups, bench, run, plank. I'm just gonna be really general with those. Right, how do we find standard deviation?
Equals STDEV.
Right, and then we just put in our push-up data. Right, mean, we kind of already went over, that one's average. Whee. Okay, and then how do we calculate coefficient of variation?
Divide these two.
Yep, and multiply by 100 to get a percentage. Right, oh crap, it went away again. Okay, so let's say this is 19%. I'm gonna make these a little less busy by decreasing our decimals. All right, but once we get these general calculations, all we have to do is copy them over. All right, so which of these variables has the greatest variability?
Push-ups.
Push-ups, right? Because it has the greatest coefficient of variation. Right, so in the given context of the measurements that were collected, it had the highest degree of variability. Okay, so push-ups will be our answer. Okay, and then assuming the data is normally distributed, what is the probability that a random person from this sample would be able to run a mile between something and something? So let's pick, I think the mile run times vary between 7.6 and 12.6. Somebody pick a value between 7.6 and 12.6.
8.5.
8.5. Okay. Somebody now pick a value between 8.5 and another value that's less than 12.6.
10.4.
Okay. I love the use of decimals. All right, so I put in here, we're assuming we have a normal distribution, okay? So if we put, these are kind of the key words. You assume you have a normal distribution, you're looking for a probability or percentile, or estimating a percentile or probability. That means we are using what? We just used one. Z-score. Yes, Carolina. Well done. Right? So we could use a z-score to figure out what percentage or what probability lands at or below 8.5. We can use a z-score to figure out what probability lands at or below 10.4. And then taking the difference between the two will tell us the percentage that lies between. Right, so I'm going to attempt to draw this in the best way that I can. Okay, so we have normal distribution, woo, right? Our mean is going to be in the center, okay? So we need to find that out in order to calculate our z-scores, right? But our mean will be in the center. And then let's say, well, let's not mark this yet because I don't want to have to erase it. So we need, or let's say we have x1 and x2. Those are kind of like the raw points we're starting at. And then we need the mean, we need the standard deviation, and then we need to calculate our z-score for each of these values. So actually, I'm gonna do let's do that. A little bit of a different organization, but hopefully this makes a little bit more sense. Okay, so our x1 value is 8.5, right? So I'm just gonna put that in here. 8.5, our x2 value is 10.4. Okay. We need the mean and standard deviation at which these two values exist, right, within their distribution. So our mean, again, we know how to calculate, and we're looking at mile time. So that'll be the data we insert in our formula. Standard deviation, again, we covered. Does anybody remember the calculation to find the z-score?
Raw score minus the mean, right?
Yep, raw score minus the mean. So let's do it for x1 first, right? So 8.5 minus the mean, and then
Divided by the standard deviation.
divide by the standard deviation, right? And then we would do the same thing over here. Raw score being 10.4 minus the mean divided by standard deviation. Why do you hate me? Oh, because I typed in standard deviation. That's stupid. Ha ha. Okay. So we get these two, whatchamacallits, z-scores, okay? We're assuming a normal distribution, okay? Our mean is 10.5, right? And you guys can all see this, right? I'm gonna move a little bit closer. Okay, so our mean is 10.5, and our standard deviation is 0.987, right? So we could label this in the sense that we're adding 0.987 each time, or we can refer to it as this is +1 standard deviations, +2, +3, 1, 2, 3, -1, -2, -3 standard deviations, okay? And we're saying our z-score for 8.5 is at -2.05. So approximately over here, right? So this is 8.5, right? And then our other z-score was -0.13, okay? So relatively close to the center, okay? Minus side, not plus side. Ah! Okay, so it actually be on this side. So this is 10.4, right? So what do we do now?
So we're trying to find what's in the middle, right?
Exactly. Right, so this is our desired percentile area that we're trying to get. So how do we figure out what that is? There's a table that could help you.
So wouldn't you find the
Take the difference of the two divided by the standard deviation.
Yep. Right. Well, not the difference of the two, but you do have to take the difference of something. Okay. So let's say we use blue. Ooh. Okay. From 10.4, right, this z-score is going to give us the area or probability to the left of this given score, right? So that's kind of going to be all shaded area to that direction, all the way to the end of our distribution, okay? The z-score that we got at 8.5 is going to give us the area to the left of that score, right? Because z-scores always give us whatever the probability is to the left of a given score. So what we have to do is we want, I don't know if you guys are able to differentiate purple from blue in your video, but we want this section, right, or this middle part minus what the area would be on this side, okay? So we really only need, right, whatever the probability is of 10.4 to the left minus what the probability is from 8.5 to the left, right? So we can do this by using our z-table. I'm going to share that real quick. I'll share my desktop. I think that would be easier. Okay, so we have for 8.5, our z-score was negative 2.05, right? So that would take us to our negative z-score table. And we go negative 2.0, 1, 2, 3, 4, 5. So we have a probability of 0.0202. That was my red marker. All right, so from here over, it's 0.0202. Okay, and then our z-score at 10.4 ended up being negative 0.12. So again, we're going to be, well, actually, we could round this up to negative 0.13. Okay, so finding that on here, negative 0.1, and this is 0, 1, 2, 3. So we have a probability of 0.4483. Okay, so let me stop sharing for a second. All right, so when we look in here, we have probability to the left of 8.5 in our distribution is approximately 2%, right, or 0.0202. The probability that somebody scores at or lower than 10.4 is about 44%, or 0.4483. Right, so to figure out, we have this whole area over here, but we only need the middle section. So all we have to do is subtract probability of the big area, right, minus the probability of the small area, which is 0.0202. Okay. So that should give us what? I don't know if somebody calculated it or not. I can do it too. 0.4483 minus 0.0202 gives us 0.4281. Did other people get that value? Okay. So we could say this as a representation of the probability, or we could say 42.81%.
So you didn't have to divide by standard deviation?
Sorry, what?
You didn't have to divide by standard deviation after that difference calculation?
No. So what we're doing is we're saying we get the z-scores by using the mean and standard deviation already. At those z-scores, we have certain percentiles, right? So if I complete this part here, the percentile that 8.5 would be at is that, right? The percentile that 10.4 would be at, we said was 0.4483. So taking the difference between these two is all we need to figure out what that middle shaded region is.
Is that because you already calculated standard deviation? I'm just confused because on the equation sheet that you have for it, it shows, maybe I'm reading it wrong, but yeah.
This one?
Yes.
So this is just to calculate the z-score.
Only.
Yeah. So once we calculate the z-score, that's when we have to go into our z-table. And these numbers in here represent the probability that a given value at that z-score would occur.
So that's just another way of doing it?
Yep.
Would that calculate with that equation that you have up there?
Wait, equation where?
The calculation we were just talking about with the x minus x over st.
Yeah, that's how we calculate these two values.
And then you grab those values and put them into the z-score table.
Yep. And then the z-score table will tell us what the probability is, right? Or the area to the left of our given value in the curve. Right? It tells us what our probability is that that value would occur. And then when we've got an in-between, so I'll stop sharing again, we take all of the area, right? Or the largest area minus the smallest area to get the middle section.
And is that table are we just gonna pull it up as we're taking the test?
Yep.
Or is it gonna be provided on the test itself?
No, you guys will have the ability to pull it up.
And then are you using Lockdown Browser as well?
No.
No, okay.
No, I used it last semester, and because you guys have to use SPSS, you have to use Excel, like you cannot use SPSS with Lockdown Browser. And I was like, that really defeats the purpose of the class, because that's part of your learning objectives. So last semester it didn't matter as much because we had pretty much finished most of our big exams, but it was really difficult because I had to use online Excel spreadsheets since people couldn't access spreadsheets on their own computer because Lockdown Browser won't let you leave the browser. And that meant I had to make like 30 different exams, and that was way too much. So I was like, we're just like, you guys are on the honor system. So I know most people are working from home, and I'm hoping that, cheating doesn't happen, but yeah. So our last spreadsheet is on squat data, and it says, in evaluating the distribution of the squat data, how would you describe the shape of it, and how do you know? Okay, so what calculations would we use to look at the shape of a distribution?
Would we have to find the skew? And
Yeah, right. Skewness and kurtosis. So this is going to be I'm gonna hide these cells. See if that fixes my problem. Okay, and then I'm just gonna erase all of this. All right. So we need to find our skewness and kurtosis. Okay, so if I do skew, or my sample skewness, right, I'll have a standard error of skewness, and then I'll have a z-score of skewness. And then I need to do the same thing for kurtosis, because I'm asking what the shape, right, is. I'm not limiting you to calculating one or the other. Okay, so calculating the sample skewness is going to be the same procedure that we used before. And we're using our squat data. Right. Standard error, again, is the square root of 6 divided by however many values we have in this given set. Yes, thank you. Okay, and then we need to divide, right, sample skewness by standard error to find our z-score of skewness. Oops, there we go. Okay, so based on this value, is our sample positively skewed, negatively skewed, or relatively normal?
normal.
Relatively normal, because this value, the z-score, is between -2 and +2. Okay, so in terms of kurtosis, we're looking at the number of outliers we have. Okay, we can calculate these. What am I doing? Square root of 24 is the constant for the kurtosis one, and then we're doing the same count function. Yes. Okay, same thing, z-score of kurtosis is just going to be sample kurtosis divided by standard error. So based on this value, do we have positive kurtosis, negative kurtosis, or is the shape relatively normal?
Normal.
Normal, right? Because again, it lies between -2 and +2. So in this case, when we're describing the shape, we would say the squat data is relatively normal. And then we justify why. It's because the z-score of skewness and the z-score of kurtosis are both between -2 and +2. You could say z-scores or standard deviations, either one is correct. Okay, I'll just put or so you don't, or standard deviations. Okay. You could also say it's in our acceptable range between -2 and 2. Okay. There is some cases, let's say this was 2.3, right, or skewness was 2.3. You could have relatively normal, a relatively normal distribution in terms of kurtosis. So in that case, you would say there's positive skewness with no kurtosis. Okay. So that's an option. Next one says, which sport has the highest mean max knee flexion angle? Easy way to find this is to calculate the mean, right? But we would have to do this for each of our sports, right? So actually, before I do this, we have over here cycling is 1, rowing is 2, mountain running is 3, and all of these should be organized based on the sport they belong to. Okay, so I'm gonna zoom out real quick. If we've got cycle, run, row, did I get, oh, row and running. I'll put them in the same order so we don't get confused. Okay. So in this case, we would say the average of our cyclists for knee flexion would be any value that has, right, or knee flexion angle that has a value of 1 paired with it. Okay. Rowing, we would do a similar calculation where we're taking the average of knee flexion angles for anyone who has a value of 2. It goes to here. Right, and for our runners, we would be looking at an average of anyone, right, again, knee flexion angle that has a label of 3. Okay. So which sport has the highest mean?
Rowing.
Rowing, right? Easy peasy lemon squeezy. And then what's the sample standard deviation of experience for the rowers? So specifically for rowers, right, we can do standard deviation. And then under experience, right, rowers are represented by the value 2. So in the experience column, we just calculate standard deviation for anyone who has a label of 2. Okay. So in this case, our value is 1.28. Let's round up. Okay. And then our last question is saying, assuming the data are from samples that are representative of the population, estimate the percentile for a mountain runner that can squat 122% of his body weight. So estimate means we're using what to calculate the percentile? Idea?
Z-score?
Z-score, right? So we need to use a Z-score. In order to calculate a Z-score, we need mean and standard deviation, right? So if we're looking at our runners, we already calculated the mean, so we could easily calculate the standard deviation, right? Runners are labeled 3. So if we go to squat data with a label of 3, okay, should be able to figure this out. Oh, and actually this was the mean for our knee flexion degree. So I'm going to change this to, hey, why don't you highlight? Oh, there it is. Runners, and instead of the knee flexion, I just want to change it to my squat data. Okay, so I'm using these bits of information to calculate my Z-score, right? Where I do my raw score, which I'm saying is 122, minus the mean, divided by standard deviation. So I have a Z-score of negative 0.56. Okay, what do I do with that?
Write it on the Z-source table.
Yep, we got to look it up on the Z-table. Right, so Z-score negative 0.56. We'll look on the negative Z-table at negative 0.5, and then this would be 50, 51, 52, 53, 54, 55, 56, right? So we have a probability of 28.77. Okay, and just to make sure we know that we're using that value right, we're estimating the percentile at, right, this percentage of body weight. So that would be our answer, right, 0.2877 as a probability, or we could write it as 28.77%. Okay, so again, I just want to reiterate kind of the take home, because I think that's like the biggest point of confusion is what to use to calculate your percentiles. Okay, so percentiles are calculated 2 ways. One way is by using your distribution calculations or your formulas, or we can use Z-scores. Okay, we're gonna use the distribution calculations, right? When we have wording like you want the exact percentile. Jesus, I cannot spell. Exact percentile. No assumption of a normal distribution, right? We would use Z-scores, however, when we use words like estimate, assuming we have a normal distribution, and this is for if we're working with a sample or a population. Or if I use terminology like find the probability, because we get our percentiles as a probability in the Z-table. Okay. A lot of times too, you'll have situations in this one where you have to find percentile below, at, or above a given raw score. Or I could also say between 2 raw scores, right? So percentiles at, you can use both the distribution and the z-score, right? At being a little bit more specific to a distribution, but similar to this case where we say like, what's the percentile for someone who can squat, right? 122%, we're saying what's the percentage or probability they can squat at that percentage, but we're estimating because that's the word I used, right? So in the case that we said find the exact percentile for a person or a mountain runner that can squat 122% of his body weight, in this data set, we would use our count if function, right? And then we would say what values are less than or equal to 122 in the squat data for mountain runners, right? And then finding how many mountain runners we have total and dividing our cumulative frequency by our number of mountain runners could also give us a percentile, but that would be the exact percentile instead of an estimated percentile. So wording is important, but hopefully that makes sense. Okay.